Continuing our work, we're moving on to problem number 29. Problem number 29 is another gas law problem. It states the following: an airplane passenger has 100 cubic centimeters of air in his stomach just before the plane takes off from sea level airport, telling you the pressure. What will the volume be of air have at cruising altitude if the cabin pressure drops to 7.50 times 10 to the fourth? So the second pressure is 7.50 times 10 to the fourth. The first pressure is sea level, 1.01 times 10 to the fifth. And we have a first volume of 100. Now, you don't really have to change this to atmospheres because basically you can use Boyle's law here. And Boyle's law states that P1 V1 is equal to P2 T2 V2, if the temperature is constant. And the temperature is assumed constant because the person's body temperature is assumed not to have changed. So that means that V2 is going to equal P1 V1 over P2. And so you can put 1.01 times, 1.01 times 10 to the fifth times 100 divided by 7.50 times 10 to the fourth. If you do the math here, you get 133 cubic centimeters. 133 cubic centimeters. Okay, the next problem, problem number 37. And problem number 37 states, what is the gauge pressure in a 25-degree centigrade car tire containing 3.6 moles of gas at 30 liters of volume? Okay, so you're going to start out, you're going to want to know P. In the equation PV equals nRT, you're going to want to know P. Okay, so P is going to equal nRT over V. And it tells you that there are 3.6 moles of gas that are, and I'm going to use my old favorite, 0.0821. So that means the answer is going to come out in atmospheres. The temperature is 25 degrees or 298. And the volume is given as 30 liters. And so P, if you do the math here, you get P is equal to 2.94 atmospheres. So the gauge pressure is going to be that number minus 1. So it's going to be 1.94 atmospheres. Now if you want to know that in anything else, if you multiply it by 1.01 times 10 to the fifth, it'll tell you what the pressure is in pascals. If you multiply that by 760, it'll tell you the pressure in millimeters of mercury. B says that you're going to add an additional, let's see how it says it. It says you're going to add, what will the gauge pressure be if you had 1 liter of gas that's at originally atmospheric pressure at 25 degrees, and you assume that it stays at 25 degrees and that the volume remains the same after you've added. So the way to do that is to figure out how many additional moles that little bit of gas you're putting in represents. And so N is equal to PV over RT, and you're adding 1 liter of gas at 1 atmosphere, 0.0821 for R, and 298 for the temperature. So the amount of gas you're adding is 0.0409 moles. And so you do this calculation again, except you add this to the number of moles. So that's going to be 3.6409 times 0.0821 times 298 divided by 30. And when you do that, you get 2.96. So the new gauge pressure is going to be 1.96 atmospheres. So adding that little bit of gas in increases the pressure by about 0.02 atmospheres. Now, answering the questions briefly on phase changes, the first question says that people use a pressure cooker to cook things faster, and it's asking how does that work, or why does it cook things faster? And basically, it allows the temperature to be raised above 100 degrees. And so you're basically boiling water at a level higher than 100 degrees because you're increasing the pressure. And because the temperature is more than 100 degrees, it cooks things faster. The next question asks, at what pressure, what is the vapor pressure of solid carbon dioxide, dry ice, at minus 78.5? And then on the next page, if you look at this phase diagram, you'll see that at minus 78.5 degrees, the pressure is 1 atmosphere. Number 17 says, can carbon dioxide be liquefied at room temperature 20 degrees centigrade? The answer is yes, because if you look at the phase diagram, there is an area where it exists as a liquid above pressures of 56 atmospheres. And then the last question is number 18. Oxygen cannot be liquefied at room temperature by placing it under large enough pressure to force the molecules together. Explain why this is. Basically, on the phase diagram, there is never a place at room temperature where you enter a liquid phase. The molecules can never be brought close enough together to become a liquid at this temperature. This is what's known as a critical point or a critical temperature. The next problem, and the next 4 problems we're going to do are all based around relative humidity and evaporation and boiling. And the first problem we're doing is problem number 51. Problem number 51 says, pressure cookers increase cooking speed by raising the boiling temperatures. Increase cooking speed by raising the boiling temperature of water above its value at atmospheric pressure. A, what pressure is necessary to raise the boiling point to 120 degrees centigrade? Well, if you look at the table, you'll see that the pressure at 120 degrees is 1.99 times 10 to the 5th pascals, or 1.97 atmospheres. And again, this would represent a gauge pressure of 0.97. That is, once you subtract the 1 from that. The next problem we're going to do is problem number 55. And problem number 55 is a problem of relative humidity. And relative humidity in percentage is equal to the vapor density at any particular temperature divided by whatever that density is if it's 100% saturated. So the saturation vapor density at that temperature, and that times 100. So the first question is, what is the relative humidity on a 25-degree day when the air contains 18.0 grams per cubic meter of water vapor? So the vapor density they give you is 18.0 grams per cubic centimeter. And if you look up 25 degrees, you'll find that the saturation is 23.0 grams per centimeter cube. If you multiply that ratio times 100, you get 78.3% relative humidity. Problem number 60 basically is the same kind of problem. We're just changing what we're looking for. In other words, they want to know if we know the relative humidity, can we calculate the vapor density? And in this case, it says if the relative humidity is 90% on a muggy summer morning when the temperature is 20 degrees, what will it be later in the day when the temperature is 30 degrees? Well, you have to see what the vapor density is. So the vapor density, if you just rearrange this up here, the vapor density is going to equal the relative humidity over 100 times the saturation. So at the relative humidity they gave in this problem was 90 over 100 times the saturation. At 20 degrees, the saturation was 23. I'm sorry, it was at 10. It was at no 20 degrees. I'm right. And the saturation at 20 degrees is 17.2. So if you multiply that out, it tells you that the vapor density is 15.48 grams per centimeter cubed. Now later in the day, when it's warmer, you have the same vapor density, but now it's 30 degrees, and at 30 degrees, the saturation is 30.4 times 100 will give you a relative humidity later in the day of 50.9%. 50.9%. And then the last problem, problem number 63, what is the dew point, the temperature at which 100% relative humidity would occur on a day when the relative humidity is 39% at a temperature of 20 degrees? So what temperature would be the dew point, that is, where the same vapor density would represent a saturation? So again, using this equation, we take the relative humidity, which is 39, divided by 100 times the saturation. In this case, it's again 17.2, and we get a density now of 6.71 grams per centimeter cubed. Now, if you look on the table, you'll see that one value at 5 degrees and another value at 0 degrees. And if you subtract those two and then divide by 5, you see that the difference per degree is about 0.32. And if you subtract 6.71 from the value for 5 degrees, you get 0.09. So if you divide those two, you'll see that the temperature is 0.23 degrees less than 5 degrees, or approximately 4.8 degrees centigrade for the dew point. Now, if you just looked at it and eyeballed it and said a little under 5 degrees, made up a number slightly under 5 degrees, that would be fine. But if you wanted to calculate it, what you do is you subtract the two, that is the value for 0 and the value for 5 degrees, and then divide it by 5, and that tells you that the density changes by this much per degree centigrade. And then you'll see that this value, the value at 5 degrees is 6.8. So when you subtract that, the difference is this. And then if you divide this number into this number, it tells you how much below 5 degrees you have to go, which is this.